Thank you for the acknowledgement. Very good morning. We'll wait for a minute so that students can join in. Meanwhile, by any chance, Rahul and Teja Maulari are present. Rahul, roll number CS19 B1035. By any chance present? Has he joined? Not yet. Okay. How about Teja? CS18B1032. No. Okay. Okay. Jesse, when these guys join, probably you convey them to call me back, probably after evening 5, regarding Rahul and Teja. Okay. And I have 4 more students who are having less than 50% of attendance. One is Abhijit Bandela, having only attended 5 classes. Dasru Nayak, 6 classes. Soumit, 6 classes. Vishnu Nayak attended 7 classes. I can see Abhijit is present. Dasru Nayak, by any chance, is also there. Very good. Soumit is there. He's also there. Vishnu Nayak not yet joined. So Abhijit, Dasru and Soumit, you have to be regular from going forward to have that 75% of attendance. You are already in the verge of 65 to 70 if you attend everything. So just to be a safer side, and also it will be good for your pointers also. Attend the classes regularly from here afterwards. These 4, including Vishnu also. Can Jesse please convey the same thing to Vishnu Nayak, and for Rahul and Teja, tell them to give me a call. Okay, yeah. So let me share my screen. Is my screen visible? Okay, fine. So I will resume the session where I have left in the last class. So we were trying to understand, explore how to find a planarity. So can anyone quickly summarize what all we tried? Keywords are good enough. Inequality is a one keyword. Theorem, that is elementary reduction, and so on. What all we try to figure out the given graph is planar or not. Anyone? Just to have a quick refresh so that it will be in a homeomorphic. Yes, homeomorphism, correct. After that is also one thing. And are there any keywords? Definitely drawing it and trying out is not a feasible approach in all the conditions, right? When I say all the conditions, when the given graph is very complex, having more number of vertices and the number of edges. So just to quickly refresh, we can do first we can apply a elementary reduction such that the given complex graph becomes a simple, free from loops, free from parallel edges, and having a if the overall reduction comes to just as an edge or a complete graph with vertex 4, it is planar for sure. If it is a a graph, simple graph with more number of like more than 5 vertices, 5 and above vertices, and edges 7 and above, in that case, we can go with the inequality approach. If inequalities doesn't hold good, definitely we can say a non-planar graph. If the inequality holds good for the reduced graph, then comes into the picture trying to further reduce or to create a homeomorphic graph. Homeomorphic to which graph? K5 and K33. So K5 and K33 are the two non-planar graphs if the given subgraph. Why I called subgraph? Because there are series of reduction happened, parallel and series reductions, edges reductions are happened. So the given subgraph can be mapped, or probably a homeomorphic graph can be made a couple of alterations to given subgraph so that it becomes a homeomorphic to K5 or K33. If that happens, then definitely we can say it is a non-planar. These are the things we understood about the process of finding a graph is planar or not. Now moving to the next one of the important concept of under a planar graph. Why I say planar graph, we'll try to understand why this geometric dual comes into picture in planar graph. Whether geometric dual doesn't come under non-planar graph, we'll see that going forward. So before going into the definitions and the things like that, directly I will take an example and I will try to explain the concept behind geometric dual. So we understand what is geometric means. Geometric and dual also we have a fair idea with respect to the language, English language. Dual is kind of a similar, right? So what this concept is all about. So I have taken a graph A in this picture. There's a graph A. It's a plain representation of graph. The given graph, it's a planar graph. Have 6 regions or faces. So I have named it as from F1 to F6. So let us place 6 points P1 to P6, one in each of the regions as shown in figure B. So I've taken a one graph, planar graph, and it has 6 regions. Yes, vertices, there are 1, 2, 3, 4, 5, and 6 vertices, and edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 edges. So this given graph having 6 regions or 6 faces now will try to find its dual. Not just dual, geometric dual, because I am trying to represent there is an embedding on plane. There is an embedding on plane. That's why geometric representation will happen. It's not just an abstract. So we'll try to create a geometric dual for this. So for first step is to replace those regions with point. So I have enclosed this point. Now, so there are 3 steps to follow. We'll see one by one. Next, let us join these 6 points according to the following procedure. Now, these points will become vertices in geometric dual. Regions became vertices, right? How to join these vertices? Are there any norms? Are there any procedures? Are there any clear defined step? Yes, there are, and we'll see one by one. If two regions Fi and Fj are adjacent, draw a line joining points Pi and Pj. For example, considering F1 and F6, they are adjacent. Any quick answer? Are they adjacent? region F1 and F6 are adjacent? It's a tricky question, but it is equally simple. Kamesh says yes. Any other answers? F1 and F6 are adjacent? Definitely F3 and F4 are adjacent. F3 and F2 are adjacent. But F1 and F6? No other answer? The answer is yes. F1 and F6 are adjacent. Why? Why is the question? Because F6, it's an exterior region, outer region, infinite region. F6 I can write this side also. Can write this also. This whole part, whichever the region is not part within the given graph, the outer part of the region is all F6. It's an infinite region. So definitely F1 and F6 can be considered as adjacent, and it will be considered as adjacent. F1 and F6 is adjacent. F2 and F6 is also an adjacent. F5 and F6 is adjacent. F4 and F6 is also adjacent. F4, F3 is adjacent. F1 and F4 is adjacent. What is the definition of being adjacent? There should be just a one edge boundary. Between two regions, there is only one edge boundary. Then those two regions are considered as adjacent. Clear? Any doubts with respect to the adjacent word? See, I have written adjacent means have a common edge. Only one edge should be common. However, F2 and F3 are adjacent? No, they are not. F2 and F4 doesn't have a common edge. They have, right? Yeah. Okay, so coming to the first point. First step, if two regions Fi and Fj are adjacent, draw a line joining points Pi and Pj such that intersect the common edge between Fi and Fj exactly once. Okay, we understood about the given regions, adjacent regions, to a draw line. So we'll see, first we'll see all the steps, then we'll try to do a drawing, a geometric dual. We'll try to find out. Next step, if there is more than one edge common between Fi and Fj, draw one line between Pi and Pj for each of the common edge. Each of the common edges. Very important point. That's why I made it as green. What it says is, if there is more than one edge common between Fi and Fj, draw one line between points Pi and Pj for each of the common edges. What this indicates? Does this graph has a FI-FJ region with more than one edge being in common? Quick answers. I will give a hint. There is such scenario, there is such situation where there are more than one edge being common between two regions. It is possible. Visually, if you try to, then it is difficult to understand, but imagine or probably look into this graph. There are two edges being common to two regions. In such case, we have to draw a line for each of the edge. That is the statement. So I guess nobody could able to figure out. So F2 and F6, region F2 and F6 has two common edges. This is one edge and the other one is the other edge, right? If you closely look, between F2 and F6, there is not just one edge. It's a series of two edges, right? So in that case, from P2 to P6, there will be two lines for each edge from crossing from this and crossing from the other. We'll try to see with example. Okay, now coming to the third step, for an edge E lying entirely within one region. There is an edge entirely lying in one region. Draw a self loop at point pk. Because that I'm considering that region is fk, then draw a self loop at point pk intersecting E exactly once. For example, in this, what is that edge which is entirely lying in one region? So just mention that region, because I have not given a labeling for each edge. Ramesh says F1 question mark. Jesse F5 question mark. Oh, sorry. Catherine Joyce says F5. We are talking about edge. Edge becomes loop. No? So rather, let's not go to F5 now because it's already a loop. So what Kamesh has highlighted, it's correct. F1 is the region. In this region, there is an edge entirely lying. I mean, it has been present but not connected. Yes, F1 is the region. This edge, right? This edge, such edges will become self loop. Okay, such edges will become self loop. So ultimately, vice versa is also true. If any self loop is there, becomes an individual edge. For example, P5 and P6. It will just connect from P6 to P5. It becomes a only single edge. When we do a geometric dual, it becomes self loop converts it into single edge becomes self loop. Okay, or rather than single edge, I will say an edge having a pendant vertex becomes a self loop. So we'll quickly try to I have to share whole window so that I just try to draw this with the help of a basic important thing. Is this visible to you all? Hope my window is or my screen is visible. Yeah. What I will do is quickly will take line. I have joined. It has become a thicker one. Yeah, there is an edge between, because there is only one adjacent edge. So by first thing, I'm trying to draw an edge between two regions, or probably the points which I mentioned as a regions, which are adjacent, right? So correct me if I go wrong somewhere or you didn't understand. You can put a message in the window, the chat window here. Definitely from here to here as well. Can I draw? Correct. Now, this is also correct. We'll try to see now. This drawing this line became, this vertex become a pendant vertex. Can I draw from P4 to P5? Can I draw an edge between P4 to P5? Ajay says yes. Jesse says no. Kamesh says no. Yeah. Yeah, we cannot because they are not adjacent. Because there are one edge, two edges. There are more than a edge difference. It is not a, these regions are not adjacent because there is no common edge. There are two different edges which are separating these two regions. Yes. Now, what all other can be drawn? From P2 to P6, we need to draw one more line. From starting from here and become somewhere here, right? This is one more edge crossing. This is because of step 2. Now, anything left out? Think. There is many edges have been left out. P1 to P6 is not been done. Right? P4 to P6 is not been done. Becoming bit difficult to map, right? P1 to P6. Anything left out? P4 to P6, yeah. Sorry, P1 to P6 done. P4 to P6 is also done. Okay. Self loop. Joyce says self loop. Correct. Don't know the self loop will come into. Or probably I will just do a self loop. Make it thicker. Okay. Anything else? Check. This is just one edge. Similarly, this is self loop is one edge. Even though it looks double, but it is just one edge. Any edges are left out? Or probably any steps we miss? First, we draw a straight line or edge among the adjacent regions. Then, for every more than one common edge between two regions, we draw equal number of edges. For example, between P2 to P6, there are two edges in common. So we draw, it became, see, the series of edges became parallel. Geometric dual, series of edges became parallel. Now, I want everyone to count how many edges were there previously, that is in graph B. And I will say graph, this green color is C. How many edges are there in graph C as well? How many edges are there in graph B? Nine in B, 9 in C. Okay. Let me go quickly to this window. Yes. One being missed out. Now Kamesh is correcting. Okay. 10 in C. Okay. 9 in C. Okay. So first we'll try to understand how many edges are there in the given graph. So this was the given graph. Exactly same number of edges I have drawn in graph B also. The only thing is the regions became points there, right? Just to make it a vertex in geometric dual, I made that as a point. So edges are same. So this is one edge, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 edges are in A as well as B. That is for very sure, 10 edges. Now the question is, how many edges came in our geometric dual? So with respect to point P1, I will try to count the edges 1, 2, 3, and 4 here. Okay. Now with respect to Okay, yeah, correct, correct. 4. Now from this side, this one edge 5, 6, and 7. From here 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it just didn't change. How many vertices are there? How many vertices were there previously? Now how many are there? What I will do is, I will cut this probably and we'll paste it somewhere here. So that see, this C graph and this graph is same. See the dotted lines, it is nicely put into without any mess. Here we did try, we couldn't able to make it as neat as graph C. So, but it is almost the same. We did able to find a geometric dual. Now, what is geometric dual? This dotted line graph is a geometric dual of graph A. So how we did this? By following these 3 steps. What are those 3 steps? First, make the region to points from F1 to Fk regions becomes an vertices point or probably points P1 to Pk. Just a second, students. Yeah, I'm back. So coming back to what we did for the given graph G, which is a planar graph. We need to understand that. That's why we are still studying under the unit 3 geometric dual. It comes under planar graph. We'll try to understand more about can geometric dual be done for non-planar the later part of the slide. First of all, the given graph was a planar. What we did, we converted that given planar graph to geometric dual, and it is also a planar graph. Right now it has been overlapped. If we take out the dotted line or probably the green lines which we draw just now, with all your help which I draw just now. So if I take that out, definitely it's a planar graph too. Geometric dual is also a planar graph. Now, what things we observed? First of all, how we got by doing these 3 steps. We first before going to the first step, each region became a point there so that edges can be mapped. Ultimately, we should understand region becomes vertices, vertices became regions. Right? That is the first observation. We'll go to the observation in the next part. First, we'll try to understand how we got this geometric dual. First, the given graph. Find the adjacent vertices. If there is just a one common edge, make it a straight line between those 2 points or those 2 regions. That's how we build the edges with respect to adjacent region. If in the given graph, if 2 regions are adjacent but with 2 edges being in common, make it a line for each of the edge. That becomes a parallel edge. Series of edges converted into parallel edges. Now, if any edge is lying inside any region, make it a self loop. With these three steps, we converted the given graph, planar graph, into its geometric dual. Right, till now, things are clear, like what is geometric dual is. Now comes try to understand, or we'll try to do a quick observation what all things have changed by making geometric dual. So the first thing, did vertices got changed? In this case only. No, vertices didn't change. 6 were in graph A, actual vertices, and in the C, in geometric dual, again became 6 vertices. However, but is that hold good every time? The number of vertices in the given graph, planar graph, will be equal to the number of vertices in the geometric dual. I will repeat. Correct. Need not be, not necessarily. So I will repeat my point. In a given graph, say X number of vertices, and for that given graph, I have created a geometric dual from G to G dash or G star. In the G star, the number of vertices will be the same as X or less than X or more than X. Just a second, students. Need not be. That is the right answer. Need not be. It all depends on number of regions. If a given graph G has X number of vertices and only have 2 regions, will ultimately the G star, the geometric dual, will be having only 2 vertices. The number of regions will become an vertices. Number of vertices will become a region. It's the first. We'll quickly see number of vertices became region or not. In this case, right now it is overlapping. But we'll see. That is one quick observation we made. And the edges. How about the edges? In this case, it is 10, and both the case 10. I mean, both the case means the given graph G has 10 edges, and the geometric dual G star is also 10. Yes, that's right. Kamesh and Jesse, yes. The number of edges will always remain same, irrespective of what. Geometric dual, the edges between the given graph and its geometric dual is always same. Number of edges. Any other observation made? Any other observations? Regions become vertices. Vertices became regions? Yes or no? If you closely look this graph or this graph, now probably this one will stick to it. P1, P2, P3, P4, P5 and P6 are the vertices, right? For geometric dual. Okay, and green line being a edges. Green lines are the edges of geometric dual graph. Now, if you closely observe, especially in this graph which we draw, the black vertices, we can say those are the regions. Can we say these black dots, which were earlier vertices, became region in the geometric dual? This dot between P1 and P6, P1, P2 and P6 only, right? And this dot between P2 and P6 only. and this dot within P6, P2, P3, P4, right? There is a boundary. That's why this becoming this black dot, the earlier vertices became regions here, right? So we made three quick good observations. Okay. So any questions till now? What we did? The first thing was should be a planar graph. We made regions to points. We labeled it as points, regions instead of region, points. Then we followed these three steps to generate a geometric dual. And what observations we made? Regions became vertices, vertices became regions. Number of edges kept constant. Right? Just reading is one by following. If we see this graph, following the procedure, a new graph G star, which is a dotted line consisting of 6 vertices and edges joining these vertices. Such a graph G star, that is a dotted line G star, is called a dual or geometric dual, or strictly speaking, a geometric dual. Why not just dual? Becomes an abstract, right? It becomes an abstract. We want to make it as a geometric dual, which can be represented or embedded in plane. It's a geometric dual. Clearly, there is one-to-one correspondence between the edges of G and its G star. One edge of G star intersecting one edge of G. If we closely see, that's why the number of edges, as Kamesh highlighted, for each edge in B, we map a corresponding edge in C. That's why the number of edges will always remain same with respect to geometric dual. Now, we have so many things to observe. Okay, some simple observations that can be made out of about the relationship between planar graph G and its dual G star are: an edge forming a self loop in G yields a pendant edge in G star. Yes, we did made this observation, but we couldn't able to put that in a list under observations, right? An edge forming a self loop edge in G yields in G. Happening in our example. Series in G produce parallel edges in G star. In our example, the question, did we see this point? Edges that are in series in G? Correct. That is P2, P6. Can quickly go and see? Yeah. There are two edges being in common between region P2 to P6. Those two series edges became parallel edges in our geometric dual. Parallel edges in G produces edges in series in G star. Vice versa is also true. See, now the fifth point, remarks 1 to 4 are the results of general observation that the number of edges consisting the boundary of region Fi in G is equal to the degree of the corresponding vertex Pi in G star. And the boundary of a region Fi in the actual graph becomes a degree of the corresponding vertex Pi in G star. Can we quickly go to our previous example? Now, so considering P6 as an exterior region, how many before going to P6, I will stick to P4. P4 being a region, interior region. How many edges the region is been surrounded with? What is the boundary? Number of edges for P4? 3. Correct. There are 3 edges making the region P4. Correct. So if we closely observe, what is the degree of P4? Yes, the degree and the boundary. Boundary means the number of edges making that a region, or probably the number of edges with respect to the region boundary will make its degree in the dual graph. Right? And vice versa is also true. So let's go to P6 now. P6 being an exterior region, but however, there are boundaries, there are edges interior to that. The outer part is the region 6, but now how many edges are there? If we closely look, this is one edge, second edge, third edge, fourth, fifth. There are 5 edges in this outer, for P6, there are 5 common edges. This boundary, right? What are those? This one semicircle big edge, next this edge, and the self loop edge 3, 4 and 5. If we closely look, how many degree P6 having? Exactly 5. One more important observations under graph G and geometrical dual graph G star. Now moving to the 6th observation, graph G star is also embedded in the plane and is therefore planar. Yes, we made this observation, but we didn't put under our list. Okay. Since the given graph was planar and the geometric dual is also a planar, vice versa is always true. Vice versa is always true. Considering the process of drawing a dual G star from G, it is evident that the G is a dual of G star. Therefore, instead of calling G star a dual of G, we usually say that G and G star are dual graphs. Okay, that is what the statement observation does is, for the given graph G star is a dual, and if we again go for the G star again a dual, there is one more dual. So instead of this being a G and G star, we can say G and G star both are dual graph. Okay. Now the important thing which we partly noted it. Okay. So if N, E, F, R and mu denote as usual the number of vertices, edges, F being regions, R being rank. That's why I took F rather than R for region, because already for a given graph R stands for rank. Okay, so rank and mu being the nullity of a connected planar graph G, and if M star, E star, F star, R star and mu star are the corresponding numbers in dual graph G star, then we understand NEF, right? N equal to F star, E equal to E star, F equal to N star. How about rank and nullity? We'll see that. Right? Being this, then this we did cross-check, right? About the number of vertices becoming regions, number of regions becoming vertices, and it just remaining same. However, if you closely observe, even rank and nullity exchanged. Okay, so these are the 8 quick and important observations about the given graph and geometrically dual graph. So any quick questions? Okay, so now the point is now, yeah, we for the geometrical dual, is this a graph or how is it? Is the question. When I say unique, I have a graph, okay, and it has been represented on a plane. It can be represented on a plane, so it's a planar abstract graph. So there are 2 students, each has represented differently. Their embeddings are different, but they are isomorphic. Embeddings are different, but they are isomorphic to each other. So now for those 2 graphs which has been represented, we figure out dual for each representation or each embedding, we'll get graph. Whether those 2 dual graphs are isomorphic, are they unique? Because the 2 representation of given graphs are isomorphic to each other. Now that is the uniqueness of dual graph we are trying to understand. Okay, so quickly going to now what I meant was till now there is a graph, okay, graph having 5 vertices, 8 edges and their mappings. Okay, so that abstract graph has been represented differently. 2 distinct plane representation of the same graph. Graph A, graph B, right? Graph A, graph B. Are they isomorphic to each other? Of course, yes, they are isomorphic to each other. Okay, it's just that the projection of this rectangle, the edge E5, E6, E7, instead of projecting outside, it has come inside in this graph A. That's the only difference. They are isomorphic to each other. Now, with these 2 graphs considering, if I create a geometric dual for graph A, I will get a GA star. If I create a or generate a graph, geometric dual graph for this B, GB star. Whether GA star and GB star are isomorphic to each other, or they unique? It's a question to be answered. Any answers? Any guesses? Because only guess can be done now, until unless we understand it. Quickly moving to the next slide. Yeah. The dual of graph A and graph B. From this, for the generated geometric dual is this one. For this subgraph B, or sorry, probably for this graph B, the geometric is. Now, these 2 are isomorphic to each other is the question. Ramesh says no. Others? Anybody says yes? Jagan says no. Joyce says yes. Okay, interesting. So, anybody else says yes or no? Or we'll try to figure out. Okay, now quickly for Joycey, this is for you. Quickly, we'll try to address with respect to number of vertices and their degrees first, or edges. Vertices are 4, right? Both are 4. Number of edges will be definitely equal because these are isomorphic graph. Number of edges are same. Definitely their duals will be having similar edges or equal number of edges. So edges will be the same. So edges are same. If you closely look, the vertex, there is one vertex of degree 4, right? This is the center vertex of degree 4. Can I find any vertex of degree 4 here? Here this is 3, this is 3, here this is 3, here 1, 2, 3, 4 and 5. It's a degree 5 here. However, here I have two vertex. This vertex of degree 4 and this vertex of degree 4. Rest other 2 or 3. Here what happened? One of the vertex of degree 4 became 3 and the other vertex, instead of degree 4, it became degree 5. Yes, yes. So both graphs are not, even though the degree matches, we should check the references, whether this it can be possible that this graph having 4 vertices and 2 vertices of degree 3 and 2 vertices of degree 4. But however, we should check that whether the degree 4 in the graph, first graph, and the other degree 4, they are adjacent to each other. There is an edge connectivity direct. There can be also possible that 2 vertices of degree 4, they are not at all connected. They are semantically far. There is no common edge. Then in that case, again, they are not isomorphic. Definitely these are not isomorphic. Okay. So we did a quick check, but yeah, luckily we got that. But there are chances, what I meant, there are chances that even with the quick check, the data is not sufficient to conclude. Okay. Now, it's 10:52. I will probably wind up today's class. I will meet you in probably will resume in the next class. Any questions? No questions? If there are any questions, I will take up in the next class. And thanks students for joining. See you in the next class.